Start with your
Well,
name.
I'm John Tepe, and that's T as in Tom, E, P as in Peter, E.
Okay, and why don't you tell us about where you grew up and where you went to school and how you became involved with DuPont?
Okay. Well, I grew up in Louisville, Kentucky, which was my family hometown. Family had been there since 1794, and I was the first to leave. But as an undergraduate, I went to the University of Louisville for both bachelor's and master's degrees in chemical engineering. And then from there, I went to Yale University and took a doctor's degree in engineering, finishing in '42. In the meantime, I had worked for DuPont the summer of 1939. And when I finished in '42, they were very kind. They said, whatever kind of work you want to do, we're prepared to offer you that kind of work. So I interviewed with 5 different departments and went to work in the engineering department, which at the time had a very famous research organization which more or less wrote the textbooks for chemical engineering. I was there, as you said earlier, a year and a half and working on a wide variety of defense projects for different groups like the Naval Research Laboratory, the Chemical Warfare Service, the National Defense Research Council, the Tennessee Valley Authority, et cetera, et cetera. When I was overnight transferred to the explosives department and sent to the University of Chicago. And at the University of Chicago, I was in an engineering group under a well-known man named Charles M. Cooper. And I supervised a group of about 20 people. Well, there was more than 20 because 17 of them were GIs, people who'd been drafted but had some training in chemistry. And they were very well qualified and very helpful. And we ran 7 days a week, 24 hours a day. And they handled operating of the what we used to call semi-works facilities, in other words, small-scale facilities for doing the same thing that was done full-scale at Hanford. I'm sure you've heard from others that one of the amazing things about the Manhattan Project was the enormous scale-up from very small operations to full-scale production. And I think that's one of the ways in which the atomic experience of World War II affected industry, is instead of scaling up 10-fold, maybe 100 would be exceptional. We started scaling up tens of thousands-fold from very small data to big data, big scale of production, which is what, of course, we did at Hanford. At Chicago, we worked on a very wide variety of problems in all areas, synthesis, separations, and others, with the idea of furnishing reliable information for use in design and construction and operation of the plant at Hanford. We were only concerned with plutonium. The uranium work was done elsewhere. So we worked with all of the people in physics and in chemistry. And you've heard, I'm sure, that there's a great deal of compartmentation of the work for security reasons. You knew everything you needed to know, but you didn't know what you didn't need to know. And of course, we worked with very high priorities, so anything we needed in the way of equipment or materials we could get promptly. And I think the accomplishments there were quite remarkable. I may have mentioned that I was located in my office in Ryerson Hall. It simply happened to be where so many of the Nobel Prize winners were located. So every day, all day, Fermi, Szilard, Wigner, Compton, Alvarez, Franck, Seaborg, all Nobel Prize winners. Szilard's an exception. Phil Morrison, we were up and down the hall all day long. It was kind of a big one-room schoolhouse. Yeah. And the working or cooperation among all these people was perfectly remarkable. I mean, And it's just as easy to sit down with somebody famous like Fermi and chat the same way you and I would. We, among other things, the little engineering group ran a school, a night school, to train people who were on their way from other locations to Hanford to run the plant. And our faculty were essentially all Nobel Prize winners, Franck and Fermi and Seaborg and the others gladly accepted invitations to lecture. And they were able to talk at the level of the you might say, the undergraduate engineer. Yeah. The nature of the problems, the chain reacting pile, as you know, generates an enormous amount of heat. And dissipating that heat, keep it from melting down, as they say, was a big engineering problem. So we did a lot of work on that. And then, of course, we were trying to increase the yield and increase the purity of the product. And so we were seeking optimum operating conditions, for example, in the separations area. And some of the early operations were pretty awkward, and we were seeking more efficient ways of doing the separations and the synthesis. We used the West stands for a lot of our experimental work. One of the reasons is that we had great headroom in the stairwells, and you could put in a separating tower, liquid extraction or something like that, maybe 100 feet tall. And of course, the story is famous about the first chain reacting pile in the double squash court. So it was kind of interesting to be playing squash in the singles court next to the doubles court in which they were running this graphite moderated pile. We also had experimental facilities south of 63rd Street, which was an old brewery that we called B Factory. And in there, we did a lot of our experimental work. There's an awful lot of things going on at one time, and everybody had a well-defined program and a problem to work on, and there was exceptional cooperation. I never ran into anything else but ready cooperation. And you could argue with these Nobel Prize winners just like the guy at the next desk, and sometimes you'd win.
That's great. So DuPont was there for the express purpose of building that Hanford plant, figuring out
Yes,
how it
that was
would
our
work, how to
focus.
cool it.
Hanford was our focus. That's correct.
That's right. And from your,
Can you pause for one second? Sorry.
me,
Yeah.
when you, even though Tom might have taken
I
question.
didn't have it turned on. I just wondered if there was any, you could shed any light on that, the problem with the B reactor not
In the
coming up
xenon.
to speed, or having the xenon poisoning and.
Yeah, I heard you mention
Because
that.
it was overbuilt. I mean, Crawford, Greenwald, and DuPont engineers lobbied to have that built
Well,
bigger.
Yeah.
And maybe you could talk about the design, since you were involved in design, was there, maybe about the DuPont design philosophy, as, you know,
Yeah.
because it
Oh.
really saved the day by,
Yeah.
the corporate culture was to build things bigger, right?
I think you have to recognize that engineering calculations are not as precise as scientific calculations. Yeah. Engineering.
Start again.
All right, you have to recognize that calculations made by engineers are not as precise and not as calculations made by physicists to get down to the fourth and fifth decimal place. And engineering always has in mind, before anything else, safety, so that we always make very careful that our results are on the safe side. And all of the design calculations for boilers and pressure vessels, piping, and all that sort of thing are always safe side calculations. And I can tell you interesting stories about that. But a 10% or 15% over design would be not be uncommon in engineering work. And that may have been what they ran into in this problem in the reactor, which I did not participate in or encounter.
You were involved in the chemical separations work.
Mm-hmm.
And can you tell us something about the design of the tea plant?
T-plant.
Right, the chemical separations plant, and the use of the remote control and the jumpers and things like that.
Well, what we did, we had in the in Chicago, we had small scale, actually manufacturing facilities. Our product would be contained in a test tube, but of course the product for Hanford wasn't much more than that. We ran the fractional precipitation process under all kinds of different conditions to try to establish optimum conditions for running it. And then we worked on alternatives to the precipitation process. One of them was liquid extraction, in which we use these tall towers in the stairwells of the football stadium. The work with the chain reacting pile in the doubles squash court had been done a year earlier than our work. And I think they were still doing experimentation. I don't know what it was. I didn't work on it. If we didn't need to know, we didn't ask. All of our work on separations was with Glenn Seaborg, and he was a very impressive chemist. We'd sit down in the morning and plan experiments sit down Monday maybe, and plan experiments for the week. And he'd give us his guesses as to what answers we'd get. And it was quite remarkable how often he was right on the button. So in that respect, you could say, well, you were confirming what was expected or what was predicted from theory. And again, as I said before, it was just quite remarkable the way theory was proven out in practice on this whole project. As somebody said, it was just a chain of highly improbable coincidences that made the whole thing work. And,
Do you think, reflecting back on the Manhattan Project and its success, a lot of people say, well, we have a problem with global warming, or we have a problem with finding a cure to cancer. Let's have another Manhattan Project. Could it be done again?
yes, I think it could. I've
Yes,
heard.
could you start by saying, I think it could be done again, or
The
what it is?
Manhattan
Because
Project.
you won't hear her question.
Oh, I see.
Yeah.
Well, in answer to the question, could an effort of the magnitude of the Manhattan Project again produce exceptional results? And I think the answer is absolutely yes. The focus on the plutonium and uranium project production was absolute. We had unbelievable talent. We had priorities for materials that were just absolute. We could get what we wanted and needed. And when it got into the construction phase, we had, you might say, unlimited resources, both of technical and management and crafts. There's no question if you could have that kind of concentration again, you could do wondrous things. Now, whether we could cure cancer or AIDS, I don't know, but that kind of focus, which was absolute, just produces perfectly remarkable results.
What was it like to be part of this during the war, when your buddies were off in the trenches of Europe? What did that feel like?
Well, that was interesting because, as you say, graduating class in engineering, essentially everybody went into the service, everybody who was physically fit. And it was kind of a mystery for anybody to be around, 25 years old and physically fit and not be in the service. But the question really never came up because I think it was understood that some people had critical jobs to do, and they were doing it. came up, for example, if you had to cancel a lease, which I had to do when I left Chicago in 1945. The landlord could say, well, wait a minute, you're responsible for another 6 months' rent. And I remember on that occasion, I said, take a good look at me. I said, I'm 26 years old at the time. I said, I'm physically fit. I had 4 years in the ROTC, and you see me in civilian clothes here now. Do you want to let this question get beyond the two of us? And he said, oh no, forget it, yeah. But mostly, the question really never came up. I think everybody understood. Almost immediately after I returned to commercial work, I was drafted. And when I turned up for induction, they said, it says here that you're married. And I said, that's right. And he said, well, go home, we don't want married men. And as I say, I had tried desperately to get commissioned, not only when I finished college, but when I, during the 2 or 3 years of work, because I wouldn't have had to be explaining to the draft board all the time, or have anybody else write. But they always just said, forget it, do your job, we'll take care of that. Do your job, we'll forget it. But then I went up to South Ferry in Lower Manhattan and was ready for induction. But I was quite happy to go in. My brother-in-law was a prisoner of war. My wife's uncle was a prisoner of war, and everybody in the family, other than me, was in the service. I was quite happy to go in. As a matter of fact, I wanted to. I wanted to be commissioned because I thought I'd earned the commission.
What about jumping around a little bit, talking about the what was known about the physical hazards of plutonium and the separation process?
Well, the information we had was that it was as hazardous a material as existed. It was tremendously poisonous, and we treated it as such. The problem that we faced a good deal was the radiation problem, because we were handling radioactive materials all the time, and we wore badges which would indicate when we were overexposed, and from time to time one of us would get a couple of days vacation to let our blood count get back in line. But we were very, very careful, and we had shielding, and most of the operations were conducted by remote control with optics to observe what was going on. And I don't know of any serious accidents in the operations at Chicago.
Could you talk about because this just occurs to me, could you talk about the scale of what you were doing in Chicago and how that translated to the scale of, say, the T plant, which was the first really separation?
Yeah.
And because that was an order of several orders of magnitude.
That's correct. I used to know all those figures. I don't remember them anymore, but it was far beyond any previous practice. The equipment we worked with was the kind of thing you'd see every day in a brewery or a food processing plant, relatively small.
Could you do me a favor? Start again. And remember that we're not going to hear anything, so you have to mention the word plutonium and working in Chicago and as opposed to scaling up.
Sure, okay. Well, with respect to the scale of operations, the engineering group at Chicago was not working on the bench laboratory scale in capillary tubes and under microscopes. We were working at a larger scale than that, but still not remotely at the scale of the Hanford plant. The vessels that we used might, if we had a tower, it might be 6, 8 inches in diameter and maybe 100 feet tall, whereas a similar piece of equipment at Hanford would be 20 feet in diameter and still 100 feet tall. the material we produced, the only time I've seen plutonium was in the bottom of a capillary tube, and it's about a quarter an inch of white powder, plutonium oxide. Later on, of course, we had to make kilograms in order to provide an explosives material for military devices. I have never been to Hanford. I've been to Oak Ridge. I've heard a lot of figures about how big everything was and how many acres it was spread over, but I didn't see that. I fully expected to go from Chicago to Hanford, but just like the draft, they said, we don't need you out here now. We'll go on back to Wilmington and get back to commercial work for the DuPont Company, which I did. But the scale-up was enormous, and as I mentioned earlier, that was one way in which the project, the Manhattan Project, impacted industry, is we changed our ideas about how far you could scale up from a small operation in the laboratory, or as we say, semi-works, to a commercial operation was greatly increased. And from then on, and I think we've benefited greatly from the experience, we wouldn't hesitate to scale up by 100-fold, 1,000-fold. Whereas at one time, we thought that a 10-fold scale-up was big. Yeah.
So it really changed the way industry works.
It did. It had a big impact. You're absolutely right. Yep.
Did the experience that DuPont had lead it to become more involved with people in academia after the war, or no?
Well, the kind of work I was in, which for the first number of years with DuPont was research work, we had a lot of contact with university personnel. Even later we did. I would say that during my 40-year career with DuPont, we always had a very active cooperation with university people. And also because of the nature of the work we were doing, a lot of people left the kind of work I was in to go into university jobs. Bob Marshall became Dean of Engineering at Wisconsin. Bob Pigford became Dean of Engineering at Delaware. And I had a lot of good teaching offers. I taught at Columbia myself for several years. And I would say there was always, in my kind of work, a very close cooperation. After, in 1950, I guess it was, I asked to get out of research and to get into engineering, design, construction, because I felt I wasn't learning much about the commercial operations in research. It's almost like being on a university campus. And even there, we always had a year in industry program in which there'd be a couple university professors in the DuPont engineering department observing how their products, their graduates, worked in industry. And that was always very profitable for both sides. We learned from them, and of course sometimes they wanted to tell us how to run the DuPont company, but we learned from them and they learned from us. And they were usually excited about what they were doing. They stayed one full year. And a lot of my old professors showed up. Gordon Williams from Louisville showed up for a year, and others. But I would say there was always, not on a big scale, but always an active participation. And of course, DuPont and the University of Delaware are always been very close. But also DuPont and MIT and the University of Illinois, very close. We also had a lot of consultants from university faculties. We had Professor Adams from MIT for years in my organization.
Just at University of Chicago, do you remember any of the minority members who may have been part of the effort? There are 16 Afro-American scientists at the University of Chicago working on the Manhattan Project.
I can't remember personally ever working with any of them. There's quite a few females, of course. One in my group, Marion Monet, was very competent.
Do Do you remember Leona Woods Marshall?
Marshall was her last name?
She married in 43 or 44. She was Leona Woods in 43, and I think married John Marshall in 44, and then was working closely with Enrico Fermi.
No, I don't remember her. There was about 600 of us there on the campus, something like that.
Big group.
Mm-hmm.
Do you have any comments, or do you remember at all Crawford Greenwald coming to Chicago?
I would know when he was there, but
Use his name.
I would know when Crawford Greenwald was present on campus, but I never had occasion to work with him on a problem. As I said, we kept our noses on the grindstone in our own areas, and I can't ever remember Crawford Greenwald being interested in anything I was working on. Of course, in the DuPont Company, over the years, I encountered him more often.
Do you have any other, I think in terms of specific comments, I'm thinking more comments on the uniqueness of the Manhattan Project, or how you felt about, and I think we've talked about a lot of this, how you felt as serving your country. And
Well, I was transferred overnight from the engineering department, where I was working on a variety of defense projects, to the DuPont Explosives Department, and informed that my location would be the University of Chicago. I went in town to get indoctrination. The man I met proved to be my future father-in-law. I was married in 1944 while I was on this project. And I remember his words, Arthur W. Scarry was his name. I remember his words very well. He said, Jack, he knew I was dating his daughter. He said, this is a highly secret project, and he explained what it was. And he said, you'll receive a great deal of classified information. And he said, if you reveal any of that information to someone who is not cleared to receive it, that will be treason. And treason is punishable by death. That was his message. He was the administrative head of the so-called TNX organization, and then a chap named Roger Williams was the technical head. So he was responsible for all the housing and recruiting of personnel and salary administration and everything. He'd been the director of production for military explosives and had built the smokeless powder plants for England and for the American military also.
well,
Okay.
yeah, that's great.
One last real quick question.
Okay.
A lot of people feel that the Manhattan Project was just a bunch of geeky scientists up in Los Alamos, and yet there might have been 100,000 people working on it at one time. Could you just talk about that real quickly and talk about your part in it and how that felt to be?
Yeah. On the question of the project as a whole, I think it's important to recognize that producing the fissionable material and then using that material, like, say, nitroglycerin, to build a weapon, were almost like two entirely separate projects. And when people mention the atomic bomb, you almost always think of Los Alamos and Oppenheimer and Alamogordo and Hiroshima. But basically, as I understand it, what they did at Los Alamos, they received the nitroglycerin, plutonium or uranium-235, and then their problem was how to build a device which would detonate that material, in other words, create in lightning speed a critical mass, so it would create this enormous release of energy and at as high efficiency as possible. Now, within the organization to figure out how to produce plutonium, in my case, It started with the particle or nuclear physicists that you mentioned earlier, and the very basic chemical research. Then it began to involve engineering problems, and then, of course,